it's time to get started. So do we have any questions on concentration so far? None? All right. Before we get into more units of concentration, let's talk about dilution. What does it mean to dilute a solution? Water it down, add solvent, right? In most cases, just add water, because water is the universal solvent. Okay, so there's a formula that I'm going to give you that we're going to derive together. How we can dilute a solution and determine what its concentration is going to be. So the reason we do this, let's say we need some hydrochloric acid to run an experiment or do it, right? And we need a certain concentration. And then the next week we need a different concentration. And the following week we need a different concentration. Should we just go to the store, go to the chemical store and buy all those different concentrations? No. We're going to buy a high concentration or low concentration? High concentration. We talked about this already? You guys are just on top of things. Good. Just makes sense, right? Okay. So we going to buy a high concentration solution of our acid or whatever we're dealing with, and then we can dilute it into the smaller concentrations as we need it. So let's just keep it simple real quick. Let's say we have a container and we have water in it and we put some red food coloring in it. Right. Then we dilute this. Oh, that was weird. They're supposed to be the same. Whoa. Hold on. To something like that. Can you see that okay? Yeah. All right. So it's not as dark, right? We just added water. N represents the number of moles. We talked about this in the gas law, right? Okay. So it has N moles of red food coloring in here. How many moles of food coloring do we have in this one compared to this first one? Same number. Does that make sense? So we can call this N1 and this N2. And we know that N1 equals N2. We good? All right. So this is going to be our first concentration. We can call M1. And we have a certain volume we'll call V1. Okay? Did I give you this equation already? No. Okay. And then over in our second case, we have M2 and V2. We okay so far? So how do we get the number of moles if all we know is the volume and the molarity? Or the concentration? Think about that.
How do we get the number of moles if all we have is the molar concentration in the volume?
Yep.
Well, if they equal each other, you should just solve for one.
Well, sure. How do we determine what that number of moles is? Okay, this sounds like a hard question maybe. It's not hard if you use your units, dimensional analysis. You guys good at that yet? Okay, so we have our volume. What's volume measured in? Liters, okay, or milliliters, but we'll just say liters. Why? Because molarity is measured in what? Moles over liters. Okay, so what are we going to do to get the number of moles? divide by volume, so let's see. Moles over liters divided by liters. Is that, multiply liters?
Yeah.
So instead of dividing, if we multiply liters,
Just cross that out.
we can see that the liters go away and we're left with moles. Does that make sense to everybody? So we can say that our molarity times our volume is going to give you the number of moles. Good? All right. Since this is true, can we write an equation in terms of molarity or concentration and volume? N1 is going to equal M1 times V1. N2 is M2 times V2. Make sense? And so if we want to dilute it, we know the concentration we want it to, we know the concentration we start at, we know the volume we want, we can figure out the volume that we need, right? Or if we need a certain volume or whatever, we only have a certain volume of our first concentration, we can figure out the concentration of our new volume, of our new solution. Any questions on this formula? Yeah, Andrew?
So just to be sure, we're only talking liquids now, right?
You can probably do this with anything.
Gases or solids?
Yeah, just, okay, you need a higher concentration of iron in our steel. What are we gonna melt more of?
Iron.
More iron, right? Okay, now is that the same? It's gonna give us a bigger volume. We're gonna have a bigger concentration, right? But, yeah, generally, we use it for liquids. Yep. We use it for aqueous solutions 99% of the time. Yep. All right, so let's do an example. We need 350 milliliters of a 1.5 molar concentration of HCl. I always start with of hydrochloric acid because this is the only one I really have to do at my high school. Okay. So we go to the stock room, and the stock solution is 12 molar concentration of HCl. Question is, how do we make that?
It's hydrochloric acid.
Yep. HCl is an aqueous solution is called hydrochloric acid. If it's just a salt, it's just called hydrogen chloride or hydrogen monochloride, whatever you want. I think it's just called hydrogen chloride. It's an ionic compound, right? But that's okay. Okay, so what do we do? Oh, good, it changed. Remember how you guys would always say, move down or move up? I fixed it. Well, we're diluting this, right? We have a high concentration, we're making a lower concentration. So we're gonna use this dilution equation. So let's, just like any other problem, we write down what we know and what we're looking for. Okay, we're looking for this, right? We're trying to make this, so it doesn't tell us explicitly what we're looking for, so what are we looking for? So let's find out what we know first, okay? What is this? What volume is it? Volume 1 or volume 2?
Volume one.
It really doesn't matter. But if we're thinking about it in real life, what volume, what solution is it? Is it our beginning solution or our end solution?
That's what we want, so
Right? It really doesn't matter, like you said, because this equals this. Can we flip it? Sure. Okay. It really doesn't matter. So what should we call 350 milliliters? Volume 2. We could call it volume 1. We could call this our first solution. We could.
that's what
No
we're looking
problem.
for, some pipelines.
Yeah. We're trying to get to this, and we have this. So, but again, it really doesn't matter. Just make sure you don't mix this with this, right? You don't say this is our first and this is our first. Yeah, don't do that. Okay? All right, so we say V2 is 350 milliliters. That means M2 is 1.5 molar concentration of HCl. And what is this? The 12 molar solution.
M1.
That's our M1, 12 molar. That means we're looking for our V1 because that's the only one we don't know. We good? It's the only thing we can find so far. Does that tell us how we make the 350 milliliters of 1.5 molar solution of HCl? Not. I mean, it helps us to, but it's not the end, right? Okay. All right, so let's grab this equation. M1 V1 equals M2 V2. Let's solve symbolically first. Solve for V1. So let's divide both sides by M1. There it is. And if we do this for a lot of different, maybe we have to find a whole bunch of different concentrations of hydrochloric acid for a lot of different experiments, right? We solve it symbolically, and we don't have to solve it again. We're done. That's one advantage of doing it that way. I don't care if you plug numbers in, then solve. Still gives you the same answer, okay? All right, so let's plug our values in. M2 is 1.5 molar. Oh, does this need to be measured in liters? Let's find out. Volume 2 is 350 milliliters. And M1 is 12 molar. What cancels? Molarity, right? Yeah. If you want it in milliliters, we're done. We don't have to convert it if we don't want to. Because we're not just multiplying those two together. And we get 0.44 milliliters of a 12 molar concentration of HCl.
I got 43.75.
I got
0.4375?
43.75.
43?
Half 12
I learned the
milliliters
same.
here.
Well, why did I get 0.44 then?
Because you want more.
Maybe it is. Yeah, it is. I don't know why I wrote that. Okay, 44 milliliters, right? 44 point what? 43
I
point?
got 43.75.
Okay, we'll just say 44. Okay, 44 milliliters, thank you, of 12 molar solution of hydrochloric acid. Okay. Are we here yet? We're not there yet. We get a little bit of this 12 molar solution, we stick it in a beaker, and there's just this much, right? So now what? What are we doing here? Okay, good. We are using dimensional analysis, but what are we doing here? We're diluting it, right? And how do we dilute something? add more solvent. What's our solvent in this case? It's an acid. In fact, let me tell you something. If the solvent isn't given to you, what is it? Water. Okay? This is an aqueous solution, so acids are aqueous solutions every single time. Now we're going to get into acids next chapter. So there's an intro to it. So what do? We have 44 milliliters of 12 molar solution of HCl. What do? If you were doing this, and you get your little jug of 12 molar HCl and you pour it in this little beaker, oh, but I need 350 milliliters of a lower concentration. So what do? Just add
Yeah.
water. How much? Until the beaker reads 350 milliliters. So if we want to know exactly how much, if we're writing a recipe for this,
350 minus 44.
yeah, we want 350 milliliters, and we're going to subtract this because we have 44 milliliters of our 12 molar solution. Not 0.44, but 44 milliliters, and we get 306 milliliters of water. We good? Questions? And I know I'm asking you these questions, and it's like, but hold on, we didn't ever even do this before, right? Sometimes we need to just step back and look at the whole picture. What are we doing? Okay? And anyway, in general, this is what the question we're looking for. But that doesn't do us any good if we don't know what to do with it, right? Any questions? What? Yeah, let's do another example. Let's say we go look in our stock room, and we find. Let's do this in sodium hydroxide this time. We find a container that reads sodium hydroxide, and this is a base, and it's a very corrosive material, and so it's kind of faded away right here, and it doesn't tell us what's the concentration of this, right? So, okay, and maybe this isn't a great example, but so let's say we have 50 milliliters of this unknown concentration. Let's say we have 250 milliliters of this unknown Sorry, I'm just doing this in my head. No, you know what? We can't do it this way. I tried to find a real problem. We'd have to do titration. You guys, did we do titration in this class with a drop of? Maybe I didn't have the indicator for this class. Oh, okay. So let's just bag that. Sorry. All right. Let's say we have. One concentration is we have 350 milliliters of a 3.2 molar concentration of NaOH, and we only want to use 25 milliliters of this in order to get let's just say, sorry, I'm making it more complex than it has to be. Let's just say we want 512 milliliters. We're gonna dilute it to, and we wanna know what our new concentration is. Sorry, I tried to make a real problem and I couldn't grasp it in my head. We good?
So in this case, you diluted it, you added,
Yeah, how much water did we add?
you added
42. 162, right?
162.
Yeah.
To dilute
We
it.
added water. Now we have 512. Now we want to know our concentration. Okay? So we go to our formula, M1 V1 equals M2 V2. Is this on our reference sheet? I don't believe it is, so if you want it, if you need it, I mean, it's not a hard one, but you need to know it. Okay? And what are we solving for? M2. So let's label everything. What's the 350 milliliters? That's our V1. And our 3.2 molar solution is our M1. And this is our V2. Does that make sense to everybody? Okay? So let's divide both sides by V2. And plug our values in. M1 is 3.2 molar concentration, and our V1 is 350 milliliters, and our V2 is 512 milliliters. What if it was measured in liters? Can we still do it?
Yeah.
Then we better do what first?
Change.
Convert it to milliliters or convert milliliters to liters. Either one, right? That way that they cancel out. Because we don't want milliliters in our answer, we want moles over liters. Okay, and I don't have this answer. I just picked these numbers out of my head. So go ahead, calculate this. What do we get? 2.19 what? Molar concentration of NaOH. Don't just say M, because we got to know what it is. What's the substance? Are we good there? Do we need an example on our own? It's on our worksheet. Would you like to do this right now or no? I'll give you time.
Yeah, let's do it.
Yeah. So go to the last worksheet I gave you. Or not the last one. Actually, it is the last one.
This one?
Yeah. It's the more concentration units. Section 1, calculate the following dilution quantities. The one that says more concentration units on the top right.
No, this one.
Flip it around. No, it's not that one. On the very top right, it says more concentration units. Oh, did I not give this to you? Oh my gosh, you dumb guy. All right. I was thinking I gave all this to you last time.
Thank you.
On the top, see the second page. More content.
Yep, section 1.
Section one.
So what are we given in this? What's that? Are we given M1?
Which one, which number?
The first one.
How much water?
Yes, we're looking for how much water you add to 100 milliliters of a 0.5 molar concentration of sodium hydroxide if we want the final concentration to be 0.15 molar.
So we have exactly 100.
So what is M1?
And one
M1
is
is
0.5.
0.500 molar concentration of, we'll just say, yeah, NaOH. Okay. What's V1?
100.2.
100 milliliters, right? And what's M2?
0.150.
0.150 molar concentration of NaOH. And our volume 2 is?
Yeah,
Is that what we're looking for?
No, we're wanting to know how much to
No, we're wanting to know how much water to add. But do we need to find this?
Yes.
Yeah, so this is a two-step problem. Okay, you got it from here? Or should we do it together? Your call. You want to do it? You don't want to take a shot? We will do it. But if you guys, I mean, if everybody wants to, I will. I'll do it right now. But I think you working on it and trying to think your way through. If you can do it here, you can do it on an exam. So the question is, how much water
V1 over there, V2.
should be added? I won't tell you this on the exam, so look in your notes. Or have a little reference card if you need it on there, right? Is our reference card full yet?
V1 over V2 equal to M2 V2 over V2. Cancel each other.
So yeah, you're solving for V2. So Aman, tell me the formula that we're gonna use.
M1 V1 over V2.
M1 V1 over,
V2.
we're looking for V2. We want it by itself on the other side. So that means M2 has to be over, oops,
Yeah,
M2.
V2 or M2?
M2 has to be underneath. You follow? Should I do that? Should I figure that out for you? So what's the original formula?
M1 V1
M1 V1 equals
M2.
M2 V2, right?
Yeah.
So now we gotta solve for V2. So mathematically, algebraically, what do we do?
Cancel.
Divide by M2. So the M2 goes to the other side, right? Are we good there? And what do we get? Anybody done yet?
333.3.
milliliters, right? Is that our answer?
No.
That's how much NOH we're gonna have, how much of this new concentration we're gonna have. So how much water do we have to add? How do we figure this out?
V2 minus V1.
333.3 minus what we started with. Or is it the other way? No, not that one, this one. Minus 100 equals 233.3 milliliters of water. So make sure you know what the question is. That's why that's one of our first steps. What is the question asking? Because if you don't know, you're not going to get there most likely. Don't just treat this as a math class. Oh yeah, today we times it. Teacher said to times it, right? We got to think our way through this. Good?
Could you do the next one?
Yeah, sure can. Any questions on that one? Okay. Says how many milliliters, so we're looking for volume, right? Of a solution can be made, so is this V1 or V2? Doesn't matter, but we can call it V2. If we call it V2, what's M2?
12.2.
0.5 molar. Because we want to know how many milliliters of a 0.5 molar solution. Those have to go together, right? Of HCl can be made by adding water to 25 milliliters. So our V1 is 25 milliliters. Does that make sense to everybody? And so our M1 is 12 molar concentration of HCl. And we're looking for V2. So just think about what our first or our second solutions are, and then break them up. Okay, in our first solution, we got M1 and V1. Second solution, M2, V2. And it really doesn't matter which one you call 1 and 2. Okay, doesn't matter. We can call it A and B, and we can call it X and O if you want. Doesn't matter.
And in this case, the answer is whatever V2 is.
Yeah, because we want to know how much can we make, right? We add water to this. It doesn't even tell us how much we add. If it did, we would know, right? So our formula, M1V1 equals M2V2, and we're solving for V2. Divide both sides by M2. Are we good mathematically, guys? Can we do this? Okay. M1 is 12 molar, V1 is 25 milliliters, and M2 is 0.5 molar. Molarity cancels out, we're left with milliliters, so our answer should be in milliliters. If they're asking what the volume in liters is, then we got to convert it. Okay? And so we get something. What do we get?
600.
What?
600.
600 milliliters? Okay. Of what? This HCl? Of this one, right? Because it has to go with, that's our second solution, of a 0.5 molar concentration of HCl. Good? How are we feeling about using the dilution equation? Unfortunately, we did all of our practice now. Now you gotta do the homework, right? All right. Ready to move on? So no questions on parts per million, parts per billion, percent concentration. Good there? Good. Okay, let's do a few more concentration types. Actually, before we get into concentration, let's talk about equivalence. Equivalence. So we use equivalence when we are interested in only one ion. For example, if we're dealing with somebody's blood, like in your guys' profession, we want to know how much potassium or how much iron is in somebody's blood, right? Well, is there just going to be chunks of iron or chunks of potassium in there? No. What form is it in? It's going to be an ion form. So there might be iron 1 sulfate or something in our blood, right? Or iron carbonate, or iron chloride, or iron phosphate, or whatever it is, okay? But we're not interested in the sulfate. We just look at the iron ion. So we have to know its charge. Do you remember how to find its charge? What's the charge of sulfate? 2 minus. How many are there? Good, I'm glad you didn't say 4. There's no parentheses, so that's a total charge of -2. Side has to be +2, so what's the charge of iron? +1, because there's 2 of them, right? Y'all with me? Okay, so this is iron 1+ in our blood for this example, okay? And so to find an equivalent, and an equivalent is not a concentration, but it just says, okay, this is just a unit, a new unit that we're learning. To find concentration, we might call it how many equivalents per liter of solution, right? Or liter of blood, or milliliter, or centimeter cubed of blood. Doesn't have to be liters, okay? But we're looking for equivalents. So 1 equivalent is equal to the molar mass of our element, in this case iron. I should say of our ion, divided by the charge of ion. Absolute value. Why do we care? What's the absolute value mean? It's a positive number. So if it's a negative charge, well, we're just going to omit the negative. That's all. Okay? We good? So let's determine the equivalent for iron 1+. So 1 equivalent of iron 1+ equals, what's the molar mass of iron? 55.85, and that's grams per mole, right? So I guess equivalent's going to be, yeah. And that is, we're going to divide by what? 1. Oh, well, that's easy. In this case, is it always going to be divided by 1? No. So 1 equivalent is equal to 55.85 grams, and it's per mole, right? Are we good? Okay, now just finding the equivalent, that's, and sometimes we might be say, okay, let's calculate how many milliequivalents. Now, is this useful just by itself? No. We gotta say, okay, how much blood do we have? How much blood do we have, and what's the concentration in equivalents per liter or whatever, right? So let's do a real problem. Any questions on how to calculate equivalent? And that's just used as a conversion factor. One equivalent equals, and really we can, anyway, yeah, we'll get there. So let's do another example. How many equivalents of iron are in a blood sample containing 0.0012 grams of iron? And we have 50 milliliters
Continuous,
of blood.
is it continuous or
Containing. That means it has inside of it.
12 grams?
And let's say we have, let's say it's an Fe3 plus ion this time, just so that it's different. Okay, first thing we got to do is write down what we know and what we're looking for. So we got to know how many equivalents. Number of equivalents equals question mark. Okay, that's what our question is. What do we know? We know we have 0.0012 grams of iron 3 plus. And we know we have 50 milliliters of blood. What's blood? What's another name for blood in this example? Is it a solvent, solute, or solution? It's a solution, right? Because iron is inside. It's mixed in it, right? And iron, there's just a little bit of it. So this is going to be a low concentration. You with me? Okay. All right, so what do we do first? Determine how many grams per mole of iron there is in one equivalent, right? This is just a conversion factor, so one equivalent of iron is going to equal, we can just steal that number, right? Same iron, 55.85 grams. And we're going to divide it by what? Because the charge of iron 3 plus is 3. That's it. And we divide that by 3 and we get 18.61 grams per equivalent.
16.61.
Or grams equals one equivalent, right? Yeah.
Why isn't it grams per mole?
It is grams per mole. Yeah, it is. But since we know the number of grams, we can just kind of omit that.
It's 55.85 gram in mole.
Grams, there's, well, equivalent is per mole, so we kind of just combine that with equivalence. So we're just gonna say it's 18.61 grams per 1 equivalent. Good? Okay, now what do we do? I don't know, you tell us, you're the teacher. We could. We definitely could. It depends on what we want our answer in, right? If we want it per liter or per milliliter. So, yeah, we probably do want it per liter, right? So convert this into liters. 50 milliliters, 1,000 milliliters to 1 liter. And can you guys do this without doing dimensional analysis for milliliters to liters already? If you can't, no big deal. Just do it, and you got 0.05 liters of blood. Good?
Why do we want to convert it to liters? Because I thought if we're already working in small amounts, wouldn't it be more painful to use liters?
No, if we get so when we deal with the equivalents, we generally use liters. Could we use milliliters? Sure, then someone from China is gonna say, oh, that's a lot, or that's a little bit, right? So just so that we're all on the same page. Okay? Now what? Let's start here. We have 0.0012 grams of iron. And we're going to use this. 1 equivalent equals 18.61 grams of iron. So what goes on bottom, what goes on top? 18.61 grams of Fe3 plus on bottom, so they cancel, to 1 equivalent. So if the answers are in equivalents per milliliter, we could use milliliter. So to answer your question maybe a little bit better, Andrew. So just look at what the question is asking. Okay, we do this and we get 6.45 times 10 to the negative 5 equivalents of iron. Good? That's kind of a tiny number. What can we convert that to? Milli equivalents or even micro equivalents? Can we do that if we have to? Just like if it's microliters or milliliters, same thing. It's just a conversion with the prefixes that we know. So if we wanted it in, let's say, milli equivalents, 6.45 times 10 to the negative 5 equivalents, and we want to go to milli equivalents, what do? What goes on top? We want to go to milli equivalents. 1,000, just like milliliters, guys. It's the same thing, to 1 equivalent. Equivalence goes away, and now we have 0. Let's see, 1, 2, 3, 4, 5, 1, 2, 3. 0.0645 milliequivalents. And if we want to go to micro, then it's 64.5 microequivalents, right? Okay. All right. Now, what is the concentration in our blood? In equivalents per liters, or milliequivalents per liters, let's say. What goes on top? Milliequivalents. What goes on bottom? The 0.05 liters. And that's going to give us 1.29 milliequivalents per liter. Good? There's only one thing we learned here, guys. What was it?
Find how many
Equivalents. That's it. How to determine the number of grams per equivalent. Yeah.
So the original question just asked how many equivalents of iron are there. So that would be the
That would be,
6.45 equivalents or the 0.46.
so this right here, grams per one equivalent. But again, what do we use that for? It's a conversion factor.
It's just
So then we just added more to it. Says, okay, what is it? How many equivalents in 0.0012? Oh, actually, the original question is how many equivalents. This is the answer, right?
the 0.0012 grams.
And then sometimes it asks
That's the
how many
concentration.
milliequivalents, so we just convert it to that, right? So then our next question was how many milliequivalents per liter? So we kind of just did like 3 problems there, right? Any questions on this? Do you want to do another one? All right. So let's practice first. Let's practice just determining the number of let's see, or the equivalents, the grams of ion per equivalent. Should we practice that? All right. So let's say we have potassium phosphate. No, that's not a good one. Let's say we have calcium phosphate in our blood, and we want to know one equivalent is equal to how many grams of potassium? Sorry, of calcium. What do we do? What? We solve it, yes. How do we do this?
Molar mass of
Molar mass of
calcium.
calcium, because we're interested in calcium only. What's the molar mass of calcium? Is that 52? I might have guessed, remembered wrong.
How do you know that the question you asked us?
What is it? 4.10? 40? 40.08 grams. Then we're going to divide that by what? 2, because the charge of calcium is 2. Do we have to worry about this, guys? No, because it's on our group 2 on our periodic table. It's not a transition metal. Divided by 2, and we get 20.04 grams equals 1 equivalent. Good?
It's 20.0.
Do you want to figure out how many equivalents are in a given amount of blood? Or in a given amount of calcium in our blood? What?
The question you will ask just a specific calcium,
Yep.
and the question is, well, how many
How-
calcium?
What is the equivalent for the calcium in our blood?
No, it will ask like this specific.
Yep. But again, this is just a minor step to what we use it for. So let's say we have 0.05 milligrams of calcium 2 plus in our sample. How many equivalents do we have? What do we start with?
2.05
Yeah, what we know. 0.05 milligrams of calcium. And what do we do next? Convert it to grams, because we have our grams per 1 equivalent, right? So what goes on bottom? 1,000 milligrams to 1 gram. Can we just keep going?
Sure.
Yeah, so this is calcium 2 plus. Now what do we do?
20.04 grams on bottom.
20.04 grams of calcium 2 plus to 1 equivalent. We're left with equivalents. That's what we're looking for, so we can stop. 0.05 divide 1,000, divide 20.04. And I don't have this one, so what do we get?
.49 times 10 to the negative 6.
Should we find out how many microequivalents there are? How many are there? Anybody know without calculation?
2,485.
Not milliequivalents, but microequivalents. What does 10 to the negative 6 mean? Micro. Right? If you can't see that, yeah, just convert it. Just make sure you...
Oh, I did a step past.
2.49.
Are we good?
2.49.
2.49 microequivalents. Questions? Yeah.
I don't know what my question is, but it's not clicking. I know we're just doing dimensional analysis and that's the conversion factor, but what exactly is an equivalent? Like,
What is an equivalent? It's the number of grams per mole of an ion. And per charge, really, right?
okay.
So, are you wondering why we divide by the charge and all that stuff?
I guess so, yeah.
That's a great question. I don't know if I know the answer to that question.
Okay.
That's
So
just
it's
how
always
it
like
is.
What?
That's just how it is.
Yeah, it's just how it is. I hate that as an answer. I'm sorry, but that's all I don't have an answer. And it is kind of an old system, but I think it's still used. I don't know for sure because I'm not in the medical field, but. Any questions about equivalence? So the takeaway here is one equivalent equals the molar mass divided by the charge.
And then if we want to find the,
Then this is a conversion factor. And then you use it when you want to find number of equivalents, and you use that if you want to find number of equivalents per liter of blood.
One, what, one more mass of one.
The molar mass of the ion, so of ion, divided by the charge of the ion. And it's just the absolute value of the charge. We just, yeah,
If it's a polyatomic ion, do you take the molar mass as like?
the whole thing. But generally, it's going to be a metal. And so, I guess it's always going to be positive anyway, isn't it?
And
Most-
it'd just be the charge of the ion in its entirety, like.
Yeah.
Polyatomic.
If we did that, but I don't know. But what we could, essentially we could determine that, right? Any questions on this? So equivalent itself is not a concentration, but sometimes we want to know how many equivalents per liter of blood we have. Because when we test it, we don't test it with all of our blood, right? We just get a sample, we draw somebody's blood, and we send that to the lab. So anybody gonna work in the lab? That's what they would do, right? So why do we have to learn it? Okay. You're going to? Good.
Not really, but I work in the operating room, so anesthesiologists give us blood gas and we go down and give them and they will give us to receive.
Yeah.
And
So-
I have read that.
So it looks like they do all the chemistry. Woohoo! All right. Ready to move on? Any questions so far? Okay, let's go to another unit of concentration, last unit. And then we got one more thing, and then we're done. So we got two more things to cover today. And then if we have questions, we can go over questions.
I have a question, we'll jump off the
Okay,
because this is what
let's finish this first. All right, so osmolarity. You guys learned about osmosis?
Yes.
What does osmosis depend on?
Concentration of
What? Gradients? Okay, yeah, it does. But it depends on how many particles are in that solution, right? And if you don't know that, no big deal, okay? But I think you learned about osmolarity or osmosis in biology, right? Okay, so osmolarity it's just the molarity, multiplied by the number of species in solution. When I say number of species, I'm talking about when you throw salt in a solution, what happens? It dissociates. So how many species are in our salt solution?
you test a lot of time.
1 sodium and 1 chloride. You with me? because sodium chloride is a 1-to-1 ratio. But if it's magnesium chloride is MgCl2. How many particles are going to be in solution? 3. That's how, well, that's not how many particles, but that's how many species are in our solution. 3 different species. 1 magnesium and 2 chlorines. Good? So this is particles in solution. All right, so let's, so this has 3 species. How many species does NH4OH have?
Seven.
2.
Oh, right.
Ammonium is 1 plus. Hydroxide is 1 minus. It's a 1-to-1 ratio. There's just 2 species. You with me? How many species are in sugar? Trick question.
3.
1. This is a covalent compound. Do covalent compounds dissociate? No. Only ionic compounds dissociate. So if we're dealing with a covalent compound, it's always going to be 1 species. Then it's the same as the molarity.
Yeah, because it's covalent compound.
Yep. So we can write that down. For covalent compounds, in solution, osmolarity, or osmol, is what we abbreviate it as, equals our molarity. Do you understand why? Because they do not dissociate. They don't break apart. Doesn't matter how big the molecule is, it's going to stay 1 unit. Doesn't matter how small it is, it's just 1 unit, 1 species.
Molarity.
Only for covalent compounds in solution.
Molarity, yes.
Yeah, we can write it out, molarity.
Only in covalent compound.
Okay? All right, so let's,
Sorry, Victor.
yeah,
I feel bad. Sugar doesn't dissociate in water?
it does not.
Like
No.
Dissolves, but it doesn't.
Yeah,
dissociate?
so let's talk about that.
It's like-
So here's sugar right here. And this is not exactly what it looks like, but it's something like this.
Okay, yeah, we did do this.
So there's sugar, but there's a bunch of oxygens around it, right? And these oxygens around it is what makes it what? It makes it polar. Because all of these are carbons and hydrogens, right? Carbon hydrogen is nonpolar, but if we have those oxygens, it makes it polar. Therefore, the water can surround this molecule. All the hydrogens hooked to the partial negative oxygens, and it solvates it, it dissolves it. Good? So it does not dissociate, yeah.
What's the difference between dissociate and dissolve?
Dissociate and dissolve?
Dissociate is like when it's separate.
Okay, good. Great question. NaCl will dissociate into Na plus and Cl minus. Then what happens is sodium will be surrounded or solvated by a water. I'm just going to draw it like this. Is that okay? So those are water molecules. And chlorine is solvated by water as well. After it's all solvated, then it's dissolved. So this whole process is dissolving. Dissociation is just when they break apart. Yep, great question. Anything else? Okay, should we do an example of osmolarity? Okay, we have 1.0, so here's our example. 1.05 moles of magnesium chloride in 3.5 liters of solution. What is the osmolarity? So what do we got to find first? The molarity. Okay? Because osmolarity is molarity multiplied by the number of species in solution. So molarity is equal to what? 1.05 moles of magnesium chloride divided by liters of solution, right? 3.5 liters of our solution. And we get our molarity is 0.3 molar concentration of magnesium chloride. That's not our answer because we're not looking for molarity. How do we find osmolarity? Molarity times how many species are in magnesium chloride? 3. Does everybody understand that? Should we try some more of those to determine the number of species? How are we feeling? Yeah? Okay, let's do that after this. So there's going to be 3 species because when this dissociates, we're going to have 1 magnesium ion and 2 chloride ions because of that guy right there. So that's a total of 3. Good? What's that? Can't hear you. Chloride is -1. So that's going to equal 0.3 molarity multiplied by 3, and we get 0.9 osmol of magnesium chloride. Great, so what do we use this for?
For certain diseases.
I'll show you in a minute. Okay?
Just another example.
How many species do we have if this is dissolved in the solution? 2 of those and 3 of those. That's it. 5 species. Are we good with this, guys? So that's all we do there.
5 species dissolve in water
Does it make sense? Why 5?
because 2 are in 3.
3 sulfates, yep. Does this dissociate? Does SO4 dissociate? No, that's a covalent compound. Good? All right.
Sorry, you said this one doesn't associate?
Sulfate doesn't. Sulfate by itself doesn't.
Right,
But there are 3 sulfate ions that will dissociate from 2 iron ions. So we have a total of 5 particles that dissociate. Good? All right, should we take a break? Or do you want to cover this last thing, take a break, and answer questions? What do you want to do? Your call.
Right to see.
Take a break? Okay, let's take a break. Okay, we all back? Okay, last topic, and then if we have questions for the review, we can. Colligative properties. All right, so there are several colligative properties, but we're probably going to just focus on a couple of them. Just to give you what they are, we got freezing point depression. Whoa. So we've heard of this one before, maybe not in name, but what do we do in the wintertime? We throw salt on the ice, right? How does it melt it? Lowering the freezing point. Freezing point of water is 0 degrees Celsius at sea level. If we put salt on it, it makes it like -2 degrees Celsius, for example. Depends on how much salt we put on and what type of salt we put on. So what's going on?
Melting.
You throw salt on there, it dissolves, and it dissociates, right? And now we have a couple of particles. So which one's going to work better? Sodium chloride or calcium chloride? Which one has more particles? Calcium chloride. That is what road salt is. Well, there's different types of ice melt, right? But the more particles it has, the better. Yeah. So it's related to osmolarity. Yep. And if the osmolarity is higher, then so the melting point will lower more. Good? Okay, another one is boiling point elevation. And how do we do that? Water boils at 100 degrees Celsius at sea level. So you throw salt in there and it dissociates. It's going to boil at a higher temperature, get it hotter. Oh, so how do you cook your food faster? You just dump salt in it, right? Wait. But yeah, we could, but then it just wouldn't taste any good, right? Okay, the next one is vapor pressure depression. So it just lowers the vapor pressure. So what does that allow? The gas just to come out, right?
So is there like a pressure where water would still be liquid above 100 degrees Celsius?
If you had a lot of water.
Okay.
Well, no, it wouldn't. No.
No.
Sorry, I misunderstood your question. So, but water will stay 100 degrees Celsius until all the water's gone.
Right.
Yeah. So, yeah, you put salt in and what happens? It doesn't boil until higher temperature, yeah. Yep. And so when you boil water, max you can get is 100, or probably 98 in this area, right? 98 degrees, and then it stops going up until it's all boiled out. If you want it hotter, You throw salt in there, and it'll get it hotter. And depending on what salt you throw in there, if it dissociates into more particles, it's going to even raise it even higher. Good? And the last one is it increases osmotic pressure. We're going to deal with these two. So let's do an example. We good? All right, so the boiling point of water increases by 0.51 degrees Celsius per mole of solute per liter of solution. Mole per liter. So what is per mole per liter? Per molarity, right? But we're interested in molarity or osmolarity? Osmolarity. So basically, this is saying 0.51 degrees Celsius per osmolarity. And that value would be given to you if you was going to do a problem like this, okay? So we need to find the new boiling point if we have 8.56 grams of lithium chloride dissolved in 75 milliliters of our solution.
How you can use 0.51 Celsius or osmolarity?
So this is just the rate at which, or how much our boiling point changes.
No, is it osmolarity or?
Osmolarity, same thing. Yep. So let's calculate the osmolarity first.
What is it?
8.56 grams of lithium chloride in 75 milliliters of solution. How do we calculate osmolarity?
Molar mass.
What?
Oh, wait, no, that's. I'm doing, equivalent, sorry.
Molarity multiplied by
Molarity times the number of species, right? So let's find molarity. How do you calculate molarity? It's just a concentration, amount of solute over amount of solution, right? 8.56 grams of LiCl over 75 milliliters of solution. Are we good with that? Those values, those units? No, we got to convert. Convert what to what? Milliliters to liters. So 1,000 milliliters on top so that it cancels to 1 liter. Okay, we good then? Got to convert grams into moles. So 1 mole of lithium chloride has a mass of something. 41.94? I didn't do that in my head, guys. So check me, because sometimes I get it wrong, right? So grams of lithium chloride go away, and now we have moles over liters. That's molarity. So now what do we have to do? Times it by
Those species.
how many?
Two.
2. Lithium chloride just has 2 species. 1 lithium, 1 chloride ion. Good? And so our osmolarity is 5.44 osmol. Is that our answer?
Times 2?
Yeah, why times 2? Because lithium chloride dissociate into 2 particles, two species. Good? Now what do we do? We use that guy. Right? 0.51 degrees Celsius per osmol. Osmolarity goes away. And this gives us 2.78 degrees Celsius. Is that our answer? What's the question? How much does our solution, what boiling point does it change to?
What is 0.51 Celsius?
So if this is water we throw it into, what do we do with this? This is how much it increases or decreases. Increases, boiling point elevation. Freezing point depression. So freezing point lowers, boiling point increases. Good?
Would the answer have been negative if it was the other one?
No, we just have to know it lowers.
What is this osmolarity? 0.551 Celsius, and what is the bottom?
What is the what?
What is the bottom? Is it 0.5?
Osmolarity. So, yeah.
I guess I don't know what we're looking for, because wasn't the start of the question that it already raised 0.51 C?
It increases by 0.51 degrees per mole per liter. Per mole per liter, that's molarity, but what's the unit of osmolarity, guys? It's still moles per liter. What's the difference? Multiplying by the number of species. Good? So, this is how much the boiling point raises. So what temperature does it boil at? Normally, water boils at 100 degrees Celsius.
That's 102.7.
So it raised 2.75 degrees. So our new boiling point is 102.78 degrees Celsius. So just be careful you know what the question is asking. Could be asking how much does it raise? Could be. Could be asking what's our new boiling point? Does that make sense to everybody? Okay, questions? Yeah. Sorry, when I printed these out, it flipped the backside upside down. Sorry. Let's do section 5. There's really two parts to one problem here. Should we do both of them? Okay, let's start with the first one.
Is this what the study guide calls like the phase changes?
No. Does the study guide have, what does it say?
It says, number 9 says determine if a given change of phase is exothermic or endothermic.
Okay, so basically it's talking about if water goes from liquid to solid,
Oh.
is it exothermic or endothermic? Yeah,
So stuff
Okay.
we've kinda covered.
yeah. All right, so it says if the boiling point of 1 liter of water is raised 0.51 degrees Celsius for every mole of solute added. What is the final so this is asking what is the final boiling point of 350 grams of ethanol to 1.5 liters of water. Okay. So what's the new boiling point? That's our question.
Is that the first question?
Yep, on section 5. So that's what our question is. What do we know? We have 0.51 degrees Celsius per what?
Every mole.
Per 1 liter of water, per mole per 1 liter of water, right? So what is that called? Per osmol, right? Because it's determined by the number of species. That's why we use osmolarity. We good? Okay. And we also know we have 350 grams of C2H6O2 in 1.5 liters of water solution. All right, what do we do? What? Okay, yeah. 350 grams of C2H6O2. Now what do we do with that? We could convert it to moles. In the end, we want to know osmolarity, right? Should we do it all in one problem, or do you want to do one step at a time? Your call. Okay. So that's the amount of solute dissolved in 1.5 liters of solution. It says water. It's a water solution. Yeah, I guess it'll change just a little bit depending on how much we throw in. But in order for us to know what the volume is, I'd have to give you the density of ethanol. And if I don't, well,
1.5 liters.
so I guess this is slightly bad problem.
Is it solution? 1.5 liter solution.
Yeah. It's a water solution of ethanol. Okay? Yeah. Yep. Well, actually, this is not ethanol. Nope, this is not ethanol. What is this called? I don't remember. We'll just call it C2H6O2. Ethanol just has one oxygen. All right. What is that called?
Pure ethanol? It's an extraction.
Well, if you want to know what it's called, you take organic chemistry. I forgot what it's called. All right. So now what?
Molar mass.
Yeah, let's convert grams into moles. How many grams? 62.068? 62.07 grams of C2H6O2 to 1 mole of C2H6O2. Are we good with that step, everybody? Now we have moles per liter. That's great. Do we have osmolarity yet? No. We're going to multiply it by... Yeah, how many? Ah, just one. Woo, so it looks like we're there, right? C2H6O2 is a covalent compound. There's only one species. So should we just keep going from here or find an answer then start again? Find an answer? Okay, let's do it. You do it whatever way you like, okay? So 350 divide 1.5 divide 62.07. Somebody do that for me. 3.76 osmol. Okay? Now what? Now we convert it to what's the temperature increased by, right? 76 osmol. And we increase by 0.51 degrees Celsius per osmolarity. That goes away. So what's our increase? 1.92 degrees Celsius. Is that our answer? Let's look at our question. What is our new boiling point? What is our old boiling point before we threw the ethanol or the whatever it is in there? 100 degrees, right? So now raise it to 101.92 degrees Celsius. Good? Any questions on this?
How do you get over 0.1?
We added it to one. How did we get this?
No, the 1 0 find.
Because we added 100 degrees Celsius. That's our normal boiling point of water. And we added this substance in there, and it increased the temperature, the boiling point, to 1.9 by 1.92 degrees. Yeah.
Would we be given the original boiling point of whatever it is?
If it's not water.
But if it's water, we should just know that's 100 degrees.
Yep. Okay. What's the freezing point of water? 0 degrees Celsius. And that's at sea level, but if you want, they would have to give it to you if it's not at sea level. So we'll just assume it's at sea level. All right. Now, any questions on that first part? Okay, the next part says, using the information above, what is the boiling point of a solution which contains 250 grams of sodium chloride in 2 liters of water? So basically it's just another problem. Should I let you guys do that one? So all you're taking from that, from the original problem, is this, right? The 0.51 degrees Celsius per osmolarity. But basically it's the same thing, different problem. Any questions before we do the review?
Do we need to learn anything new for part 6 of this worksheet though?
Part 6, no, it's just kind of a summary of everything. Do you want to do one?
Yeah, just like the equation, like the reaction equations kind of just throw me off. I'm not sure.
Okay. So which one do you want to do? First, second, or third?
It's the first one.
Okay. Okay, this is on section 6 on our worksheet. Says, what is the volume of a 16 molar concentration of nitric acid would you use to react with 5 grams? So it reacts with 5 grams, 5.5 grams of potassium hydroxide according to the following equation.
Is it wet?
With. Sorry. So we have HNO3 plus KOH gives us H2O and KNO3. What kind of reaction is this, guys? Acid-base reaction, a neutralization reaction. Okay, so we want to know what the volume has to be in order to completely react with 5.5 grams of KOH. Where do we start?
What we know.
Yep, we know a couple of things. Where's the best place to start?
Balancing the equation.
Okay, good. We got to have a balanced equation. If we don't have a balanced equation, we can't do anything. Is it balanced?
Might be balanced.
It's already there. But yeah, good. We have to balance it. Are we good? All right. But yeah, always check to make sure that part's done. Sometimes you'll be given a balanced equation, and it looks like all three of these cases it's not balanced, but this one happens to be already balanced. Okay? Okay, we have it balanced, now what? Should we start with the 16 molar solution of HNO3 or the 5.5 grams of KOH? Does it matter?
I don't think so.
Okay. Should we start with 16 molarity?
Yeah.
Okay, let's see what happens. 16 moles, and I'm going to break it down. Moles of HNO3 per 1 liter of solution, right? Can I convert this into something else yet? We got to find volume of HNO3 solution. Always start with the thing that you know most about.
Is it 1 liter?
Because if I multiply by a volume, I can find number of moles, but I'm not looking for that. I'm looking for this guy right here. So we're not going to start here. Does that make sense to everybody? I don't know what we can do at that point. So if we start with 5.5, let's use a different color. 5.5 grams of potassium hydroxide. And what do we convert to? Yeah, we eventually got to find volume of HNO3. So let's convert that to moles, and then what? Stoichiometry. Mole to mole to get to HNO3, because that's what we're interested in. Okay, so the molar mass of potassium hydroxide is, potassium is 39.10, is it? Oxygen is 16, hydrogen is 1.008, so we get a total of 108. Did I do that right? Grams of KOH to 1 mole of KOH. Grams goes away. We still need to get the HNO3, so we keep going. What's the mole to mole ratio? 1 to 1, that's easy. 1 mole of KOH to 1 mole of HNO3. Now what can we do?
Molar mass of HNO3.
We could, if we wanted to know grams of HNO3. Do we? What are we looking for? Volume in liters. Do we have something in liters? Kind of. This is moles over liters.
Yeah, so we could do 16 moles.
So let's use that. Does that make sense? So always break down molarity into moles over liters when you're doing stoichiometry. So 16 moles on bottom, so they cancel, to 1 liter of solution. And this is a HNO3 solution, right? And that's what we're looking for so we can stop. Does that make sense? Okay. Question?
No. Unless, can you draw a picture of all of this, cause I can't imagine it.
Okay. Yeah, we have, so this is a neutralization reaction. If we have 5.5 grams, so here's our little reaction vessel, and we pour, there's our H, or KOH. So we have 5.5 grams of KOH in there. And we want to know how much of this do we put in there to neutralize it. So here's our little jug of 16 molar concentration of HNO3. We want to know how much of that we put in so that it completely neutralizes it, and then we can drink it when we're done. Wait, don't do that, but okay. Does that help?
Yeah, no, not really.
What's your question?
Well, it's with like the volumes and stuff, I could kind of like logic it out. I think like if I had a 2-liter bottle, it separated everything, whatever. But this is just imaginary numbers, making shit up, I don't know.
That's because it's just a problem, but let's see. So we know that now this stuff right here is so that we can make great predictions, really. So that we can figure out how much we put in so we don't have a lot of waste. So that's the whole point of stoichiometry. But in the end, what do we get here? Does anybody calculate this? 0.006. So basically 6 milliliters, right? All we need is 6 milliliters. I'll just keep dumping it in. That's going to waste a lot of stuff, right? And maybe this is a false problem, because would 6 milliliters dissolve all that? Maybe not, right? So it's like our watermelon math problem, isn't it? Just because the watermelon, I call it a watermelon math problem because they always have these weird story problems that have nothing. There's no way you're going to ever do that. Why would you ever do that, right?
So like, maybe goes to the store and buys like 600 water.
Yeah. But theoretically, this is what we can do. We good? So, if you don't like this bottom section, get ready. Next chapter, we're going to do a lot of this. And it's kind of putting, we're going to talk about acids and bases, but we're going to take everything, not everything, but a lot of things that we use so far and kind of use it together. We're going to deal with molarity because when we deal with acids, bases, we deal with concentrations. And we're going to use stoichiometry to go from one substance to another, and so on. And if we could even use ideal gas law if we have a gas that's involved in the reaction. So,
fun.
yeah.
I'm glad you guys.
All right. Any questions on this before we talk about the review? Oh, sorry, I didn't have leave you a lot of time for the review. Okay, questions? Did I? Hey, when you guys take the exams, exam 3, did your reference sheet have all of the the molarity and the mole roadmap that I gave you? Did it have all that? Okay, because yeah, did it have the right side of it? Okay, because in my 1210 class, I send my reference sheet to give so that the students can use, and they swapped it out for the one the department uses. Well, that's a ripoff. I wanted this one. I was just making sure that, and that's okay, we don't need it right now, because most of that reference sheet we're going to use next unit.
I think that they gave us this one.
Oh, they did?
Yeah, that was the one. They didn't have, yeah, but they didn't have the other one where it has this.
Okay, so if you guys want that larger mole roadmap, you're going to have to put it on your little reference card. So they did the same thing. They swapped it out and gave you theirs. Sorry. I tried to help. But that was the only thing added, so.
Question number 20.
On the study guide? Yeah.
Last class, you were talking about changing the test
To 23rd?
Wednesday.
Yes, I did. Yep. So you can take the test up until Wednesday, so that's right before the break. You guys know we don't have class on next Thursday, right? Okay. All right, so you said number 25?
No,
20. Oh, there's not a 25.
know how to.
Know how to dilute a solution. M1 V1 equals M2 V2. That's it. We did those examples. Does that make sense?
Yeah, now
So that's what you use for number 20. So you're going to have to dilute a solution and figure out what your new concentration is or what volume, right?
Can you do a parts per billion speed run?
Yeah.
which number?
He didn't. Did you ask a number? Or is it just parts?
That's 19.
Number 19. So know how to calculate concentration in parts per million or parts per billion. So if we have let's just say we have 30 micrograms of chloride in 30 kilograms of water. So basically, and that's basically zero mass, right? It's not, but so this is basically let's just call this tap water. Now it's our solution, right? Okay. So we want to know what concentration is. And maybe it'll tell you in parts per million or parts per billion. But either way, it's going to be the same for the first part, right? So it's just a concentration. What's our solute?
Chloride.
Yeah. And this is our solution. Concentration is amount of solute, 30 micrograms of chloride, over the amount of solution, 30 kilograms of water, of tap water, or we just call solution. Okay?
So I forget, it's kilograms, it sounds
Kilograms is, well,
But you said
kilo.
kilograms of water. Did you mean kiloliters?
No, I meant kilograms.
You did.
Yep. Can you have a weight of water? Yeah, you sure can.
Does that matter for the formula or?
If it's in liters or if it's in volume, then this better be in milliliters and this better be in what? Grams, right? If you're using mass over volume, has to be in grams per milliliter if it's a water solution, because 1 gram of water is equal to 1 milliliter of water. You want the units to cancel out for the percent concentrations and the parts per million, parts per billion. Good? And so before we can multiply by a million or a billion here, what do?
Convert
Make sure these are in the same unit. What unit should we convert them to? Yeah, let's convert them both to grams. So 1 million grams, micrograms, is the same as 1 gram. Do we follow that one, or do we not have that in our head? Because if you don't, I can do it a different way. Anybody want me to do it a different way?
Sure.
Okay, here we go. Okay, we want micrograms down here because we want to cancel them, right? And we want to convert it to grams. 1 microgram, what does micro mean? What's our x 10 to the whatever power for micro? 10 to the negative 6. 10 to the negative 6 grams is equal to 1 microgram. Essentially, that's what we do on our conversion. We want our top value to be same value as our bottom value, just different unit. Okay? But what does this mean? It means 1 over 1 million. So the way I did it before was just exactly the same thing. Okay? And then we keep going because we got kilograms. We got kilograms up here to cancel out to grams. And we can do the same thing here. 1 is equal to 10 to the 3 or just 1,000, right? So these are just numbers written in a different format.
It's all just numbers in a different format, man.
Yep. So what way is the best way? The way that you know. And if you don't know, then you better study. Really. Okay? So we got to know our prefixes from day one, almost day one, and we still need to know them. So now we see that micrograms cancels with micrograms, kilograms cancels with kilograms, and grams cancels with grams. Yay, we're on the right track. Okay? Now, it's hard for me to see to multiply by a million or a billion just by looking at this. And that's okay. Find out what our calculator tells us this is.
1 times 10 to the negative
1 times 10 to the negative 9? 1 times 10 to the negative 9, no units, right? So what are we going to multiply by? A million or a billion? A billion, because a billion is 10 to the 9 power. And if we do that, we're just going to get what? 1 what? Parts per billion. Now, I probably won't get you the same number so they cancel out, but you with me?
Okay.
And if it was closer to a million or 10 to the negative 6, then what if it's 10 to the negative 7? Still a million, because then it's just going to be like 10, right? And let your calculator do the math for you. You don't have to just be able to know that like I do, okay? But that's basically parts per million, parts per billion. Find the concentration, make sure your units cancel out, and multiply by either a million for parts per billion, parts per million, or a billion when you want to find parts per billion. Good? Yeah.
Isn't capital M and G megagrams?
Yes.
Like, so it wouldn't be like 10, 6 instead of negative?
This right here is a micro,
Oh, it's micrograms. I chose like a little M.
So that's not an M, that's a Greek letter mu. That's what we use for micro, and that is 10 to the negative 6.
Okay.
Good?
Can do it physically the other way, the numbers?
Yeah. Yep. So if we have 30 micrograms of chloride over 30 kilograms of solution. So the question was, let's do it the way I do it, right? Is that what you're asking? Okay. So micro, that's a small one. So we need so micro is a millionth. So if we have a million millionths, then we have 1 gram. You with me? And then 1 kilogram is 1,000 grams. So here I can see this is a million times 1,000 on the bottom. I can see that that's a billion on the bottom. That tells me, oh, I just multiply by a billion, or 10 to the 9 power, and all of that goes away, right? It won't always work out that way, but so then you still get 1 part per billion. So which way should you do it? Pick a way and stick with it. Just make sure you understand it if you do it my way, right? Because my way, it's not directly on your prefix chart that we made at the first of the semester. But this way is your call. Anything else, yeah, Andrew?
So for the gas laws, 3, 4, 5, I guess 6. Can we, let's see, so sorry, it doesn't mention Avogadro's law. Do we need to have that one on our card or know that?
Number 7 says, know how to determine the volume of a gas at STP. So that's basically Avogadro's law, meaning 1 mole of any gas is equal to, what is it? 22.4 liters of that gas. But that's only at STP. And what is standard temperature? 0 degrees Celsius, or 273 Kelvin, right? What's our standard pressure? 1 ATM, or 760 millimeters of mercury. Because we do need to know that conversion from ATM to millimeters of mercury, right?
1 mole of gas equal to 22.4
Liters of that same gas.
gas.
And it doesn't matter what gas we're dealing with, but that's only at standard temperature and pressure. Good? Yeah.
Does that say 22.4?
Yeah, 22.4 liters.
Oh,
Gas.
Sorry.
Can we do push?
I need to slow down, don't I? Because when I was a kid, I had beautiful handwriting. And then what happened? Rush, 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 rush. Hurry, 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 hurry. And then you just, and sorry. Okay. Okay, what other question?
9.
Number 9, and then what?
Number 11.
Okay, let's do 9 and then 11. Okay, number 9 says, determine if a given change of phase is exothermic or endothermic. So this is kind of like this. H2O as a liquid going to H2O as a solid. Is that endothermic or exothermic? Are we releasing energy or taking it in? We're releasing it, making it colder, right? So this is exothermic. If we flipped it around, it would be endothermic.
Exothermic.
Does that make sense?
Can you explain it one more time?
Yeah. So if we have water, we have a cup of water in our kitchen. This is more real, right? And we put it in the freezer. What happens? The heat releases from the water and goes out behind the fridge. You feel behind the fridge and it's warm, right? It takes the heat out of the water. If it's leaving the system, we call that exothermic.
And if you put back H2O solid?
But if we go to H2O solid, going to H2O as a liquid, then how do you have a piece of ice sitting on your countertop, How do you get it to melt? Well, you just leave it there because it's warmer out here. The heat comes from the surroundings to the ice. That's endothermic. Make sense?
Yes, thank you.
Okay, number 11 says know how to determine if a given molecule will form a solution or not in terms of polarity. Okay. So let's say we want to know if it dissolves in water, right? Does that dissolve in water? Well, how do you know right away? What? But how do you know? Because what is?
Carbon and hydrogen.
Oh, good. This is a carbon-hydrogen compound. It's not polar. But let's say, oh gosh, what if it's harder? What if it's something like NH3? Draw the Lewis structure. And I'm not going through that. Do you guys need help with the Lewis structure? So now what do? Now we determine the molecular geometry. Or we can recognize what? Oh, there's a lone pair that makes it polar. If we didn't remember that, then we draw the molecular structure of it, molecular geometry. There's our three-dimensional picture of it, right? Then what do we do to determine if it's polar? Well, we first determine if it's partial positive, partial negative, right? First of all, is the hydrogen-nitrogen bond a polar bond or non-polar bond? Yeah, look at our electronegativity chart. 0.9 difference, so it is polar or non-polar? Polar. Which side is partial negative, the nitrogen or the hydrogen? Nitrogen is more electronegative, so it's partial negative. The hydrogens will be partial positive. Can we draw a straight line that separates these? Yeah, positives on one side, negatives on the other side, so this is polar. So does this dissolve in water? Yes, because water is also polar. And if you don't know, how do you figure it out? Same way. Did that help?
It's polar.
So I may or may not give you a simple one. What if I give you one like this? CH3, CH2, 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 OH. Is that going to dissolve in water?
Yes.
Why? That part right there makes it polar.
That's a covalent bond.
Well, no, it's not.
The OH.
It's not. It's C 1, 2, 3, 4. H 3, 5, 7, 9, 10. That's what the chemical formula is. This is a covalent compound. It's written this way because that's the structure of it.
So it's
But then if I say, okay, if I have CH3CH2OH, now they're both polar. Which one is more polar? The first one or the second one? Which one is more polar? What'd you say? Here's an easier question. Which one is more non-polar? Yeah, this one has a huge non-polar section. This one just has a little non-polar section. Therefore, which one is more polar? This one's more polar.
Oh, because,
Because it has less non-polar.
and we know that OH is polar because of hydrogen bonding.
Because of that right there. And if we draw the structure, it's going to be, we'll call this R. That's all of this stuff right here, hooked to the oxygen and the hydrogen. And if we look at this, this is the partial negative, partial positive, partial positive. There we go. It is polar. They're both polar. This one is more polar.
Because it has less non-polar.
Less nonpolar section. Does that make sense? I don't know that you'll be given that or given one like that. I know my 1010 class does. Yeah, 1010 class is supposed to be easier than this class. For the most part it is, but sometimes we test them on something. Why do we, okay, anyway. Are we good?
Did you do number 10?
Yeah, number 10 says determine the amount of heat released or absorbed in a given reaction with a given enthalpy. So we might say, okay, we have, and I'm just going to pick these numbers because I don't know what they are in my head. Let's say we have sodium metal reacts with water, and we get sodium hydroxide and hydrogen gas. And is this an exothermic or endothermic reaction? We did it outside, first of the semester. What is it? We get a lot of heat, right? So we'll either be given this in a delta H value, and maybe it's negative 562 kilojoules of heat. Or it might say plus 562 kilojoules on the product side, because it releases it, right? So it'll either give it to you like this, or it'll give you this and that. And is it number 10?
Yeah.
Okay, it says determine the amount of heat released. I like this version better. So if they give you this, just know that it goes as the product, right?
Give negative.
Yeah, because it's negative. If it's positive, it's a reactant. Good? Okay, so let's say we have 3 grams of this, and we want to know how much heat is released. So we're going to start with 3 grams of sodium and convert it into what? Everybody. Moles. That's the only thing we can convert it to, right? So we have 22.99 grams of sodium. Let's practice. 22.99 grams of sodium.
So mean.
It's still messy, but okay. If I practice, then I'll get better, just like when I was 3. Okay, or 5, whatever it was. 1 mole
No, it's not balanced.
of, oh yeah, do we have to balance this? We sure do. Is it balanced? It sure isn't. So we better put a 2 right there, just to make that one even, right? Because that was even. That's always going to be even. But you said if it's everywhere, save it for last. I kind of looked at it and noticed that everything else already balances. So I kind of did. And then we have 4 on this side, so we better put a 2 right there and a 2 right there. Okay, now it's balanced. All right, so our grams goes away. Now we have moles of, what are we looking for here? Oh, heat. How much heat? So now what do we do? What goes on bottom?
2 moles of sodium.
2 moles of sodium. And we want kilojoules in the end, so how many kilojoules? 562 kilojoules, because for every 2 moles we have 562. For every 2 moles of water, we have 562 kilojoules of heat released. For every 2 moles of sodium hydroxide formed, we have 562 kilojoules. For every 1 mole of hydrogen formed, we have 562 kilojoules.
562 kilojoules doesn't just go with sodium, it goes with anything.
It goes with all of them, yeah. It's part of the recipe.
Right.
It's part of our balanced equation. Good? And if you want to go a little bit deeper than that, you take 1210, because we're going to really put that on steroids. But we're going to keep it simple in this class. And so we can see that moles cancel out and we're left with kilojoules of heat. Is it released or absorbed? Released, because it's a negative value, or it's exothermic, right? And whatever the answer is, that's how much heat is released. What is it?
36.67.
6.67 kilojoules of heat released. Or we can call it negative, right? Either way. Uh-huh.
So when it's negative, it's released?
Yes, exothermic. Then it's absorbed, and then we put this on this side if it's positive value. Does that make sense? Yeah, but it really doesn't matter either way. It's still going to be 562 in our conversion, right? Yeah. Does that help? Okay. Any other questions?
On Tuesday, are we still reviewing, or?
We could if we have more time. And if you haven't taken the exam by that time.
We studied acids.
So on Tuesday, we're going to study chapter 10, acids and bases. Yep. Okay, no questions. We still have 2 minutes. Yeah, Andrew.
I guess, earlier I asked about the gas laws, gate isn't on that list. Well, I guess my question is, do we need to know, if we know the combined gas laws, do we need to know the separate ones? Not really, right?
Even if you, and ladies and gents, if this is gonna, maybe this will help you, maybe it won't. This is on our reference sheet, right? Let's divide both sides by temperature, and we get PV over T equals NR. If the number of moles is constant, then this whole thing is constant. Then that gives us the combined gas law of P1V1 over T1 equals P2V2 over T2. Do you-
So the combined gas law is the same as the,
It's not the same, but you can get it from this equation, just like I did. And then if temperature is constant, then you have this equation. If volume is constant, then you have this equation. And if pressure is constant, then you have this equation.
How do you know what is constant?
It doesn't give it to you. I mean, or it tells you it's a constant temperature.
so, sorry, I just wasn't here last week when we talked about the ideal gas laws, so I'll just watch the video, because
Okay.
I was hoping we could go over that, but I know we're out of time, so, all good.
Whatever you
I'm
want.
out of time, I got work.
Okay, sounds good. Okay, have a fantastic weekend. Study, study, study. Be ready at least by Wednesday. But if you're gonna take it Wednesday, make sure you get it scheduled so you don't come, oh, I was gonna wait till Wednesday to schedule it, and then there's no more room. So get it taken care of as soon as you can. Take care. Thank you. You too.